Welcome to today's lecture. We stopped last time with the discussion of the capital asset pricing model, and let us now turn to the convex optimization. I want to talk a little bit more generally about optimization and algorithms for convex optimization. And later on, we will be using and applying this knowledge in MATLAB to do a portfolio optimization. But optimization and convex optimization is, of course, not only restricted to the realm of portfolio optimization. You will encounter optimization and optimization algorithms in many places in finance. For example, every time you do a statistical analysis, you will have to estimate parameters, and parameter estimation is usually done via some kind of optimization strategy. For example, maximum likelihood, as the name suggests, these are estimates that come and result from a maximization of the likelihood function, and in many other instances you also will resort to optimization tools. Okay, so let's look at this very generally. First of all, we start with a general optimization problem. We usually minimize a function f that is given as a function of a vector, of a real valued vector x. So we minimize f under the condition that x is included in a solution set S that is part of the n-dimensional real numbers. This is important now that we are looking at n-dimensional real valued functions. Why? Because in high school probably you have seen function optimization and minimization, maximization when it comes to functions in one dimension. This is very simple, but in many cases here we are dealing with multidimensional problems, and this is where it gets tricky. So we'll concentrate on these tricky examples on n-dimensional optimization in the n-dimensional real space. Please note that actually it is no problem to simply look at and to solely, exclusively look at minimization problems. Why? Because if you minimize a function, you can simply switch it to a maximization problem. How would you do it? If you want to maximize f, you simply take the minimum, the negative of the minimum of minus f. And then the minimization of f, of this function, is equivalent to the maximization of the function itself. So if you look in any computer, you will always find optimization algorithms that are documented and have documentation for the case of the minimization of f. And it's not that these functions cannot maximize, it simply is equivalent to the minimization of minus f, and then you have to take the negative value. Okay, so we are just looking at minimization problems, and maximization is simple from that. The solution of such an optimization problem includes searching for a global optimum S star that is included in the solution space, so that f of x star is less than f of x for all other solutions x in S. So this is a global optimum. If it is just given like this, this is a local optimum. Why? Because there might also be another x for which f of x star is equal to f of x, and then this would be a local optimum. And it might be that such a global optimum exists, might be that it is, well, it is unique, of course, then. Might also be that it is not unique. Then in this case, here, this is, of course, a globally minimal point, but we have two of these points. And finally, it could also be that the solution set itself is empty. And it's quite simple to think of such an empty solution space. For example, if you want to minimize f of x under the condition that x is larger than 1 and x should be smaller than 0, then you can see that these two restrictions, these two conditions are mutually exclusive, and the solution set itself is empty. And you will not find a global or local optimum. There will also be local optima, and in this case, the resulting X star is only locally optimal in the space in a certain small or larger space around X star. To show you this, there's a simple, small MATLAB program here. This is in the first line. I think this is the first time we have seen a function handler. This at symbol, at x, this means that everything that follows afterwards is the definition of a function in x. Yeah? You have a question?
It was in connection with the slide before.
Yeah?
Because, like, if we look at the case for what's the
Square root.
Square root of -1, then we have the two-dimensional case. We have no solution, but in the case if it's in an n-dimensional way, then we have this. We can get a solution. So in this case, if we exclude like the -1, shouldn't there also be a solution for this case if you exclude like x is bigger than 1 and smaller than 0?
I don't really get your question, I have to admit.
Okay,
If you want to, if I understood you correctly, if you take the square root of -1, it has no solution in the real numbers. It has a solution in the complex numbers, but that is not yet an optimization problem. It is simply a function. So if you want to minimize or maximize this, for example, let's assume you want to maximize the square root of x. You would probably include something like this in real numbers. Yeah. If you now were to include an additional condition, restriction on x, would simply mean that remember that you restrict yourself to the n-dimensional real set of the n-dimensional real valued set of numbers. And be careful, R2 is not equal to the set of complex numbers. This is why. I mean, the elements are the same, more or less, but the product and the sum operations are completely differently defined. Yeah? You need a different product and a different sum to be defined on these fields. That's what they actually call in algebra. On these fields, so that if you define the solution set to be a subset of the two-dimensional real space, then it is quite clear that there is no complex solution because you're looking in different field of numbers. Okay, so coming back to this slide, I think this is the first time we've seen a function handler. I'm now defining a function, g. G is equal to, and then this at symbol signals MATLAB that everything that comes afterwards is supposed to be the definition of a function. So g is defined as a function of x, and afterwards comes the function body. Everything that follows this at and x in parentheses, these are the operations that form the new function. So what do? Polyval 1 minus 10.5, 39 minus 5, and so on, and x. So this is a function. If I were to enter g of 15, it would mean it would set x equal to 15. It would enter 15, x equal to 15, In polyval, 1 minus 10.5 and so on. What is this? Polyval is the function value of a polynomial. The first entry here in parentheses is the coefficient vector for the polynomial, and we want to evaluate the function at point x. So this here, g of x is just minus 59.5x plus 39x squared minus 10.5x to the third plus x to the fourth. That's all. And if I were to enter g of 15, it would simply enter 15 as x and then give me the value of the polynomial at x equal to 15. Now, it's a polynomial function. Okay. And then I enter a plot x vet, g x vet, and x vet is defined as 1, double point, 0.05, double point 4. What is this? This here simply generates a vector of numbers from 1 to 4 in steps of 0.05. So this is just a vector 1, 1.05, 1.1, 1.15, and so on until 4. So this is a very short and convenient way to define a vector starting at 1, going up to 4 in steps of 0.05. And plot x vet, g x vet simply does what? I have a large set of values on the x-axis. I put it into the function g, and then I get little points, and then I tell MATLAB, please plot this. And as you can see on the next slide, this is the result. It simply gives out the plot of this polynomial, and as you can see, you have one global minimum and one local minimum. Later on, we will see that optimization strategies that are derivative-based usually will run into a local optimum depending on the start value. If we start at 3.5, it will run into the local optimum on the right-hand side. If we take a different start value, it might find the global optimum. In this one-dimensional setting, it's quite simple to find all the global optima. Again, in one dimension, this is not a big challenge, but it gets tricky in multi-dimensional settings. Okay.
Is there any problem that you just use those little steps? So it's like, might there be like the minimum might be at a step like 1.0.57 and not just 1.01?
One would have to look up the documentation for the plot function. I would assume that, that's a good one. Has everyone understood the question? The question is whether actually there might be another local or global optimum just in between these steps of 0.05 to the next. So there might be, for example, a minimum between 1 and 1.05 at 1.02. One would have to look up, there is, one can be sure about that. This is a polynomial that looks very smooth, and it's a polynomial of order 4, and there shouldn't be any oscillation in between. So I would rule that out from experience, but one would have to look up the documentation for MATLAB and the plot function, because this looks pretty much like it uses the function values you're supplying MATLAB with, and then interpolating this and just putting a smooth function through all these plots. And for us, it seems like it's a smooth function. But in reality, of course, I've only supplied MATLAB a discrete set of points, and it somehow plots a smooth function from this set of discrete set of points. But again, I would assume that just from the definition of the function and from experience, there shouldn't be. But I cannot be really sure about that. That is correct. Also, there might be a different function with which you can plot the function g itself without supplying this discrete set of points. But I think this plot function is the simplest function you can get in MATLAB. And this is only for illustration, I guess. Now we can use Fminunc. Fmin UNC, this is the standard optimization tool for unconstrained optimization. Unconstrained meaning you have only a function f and you have no constraints. So there's no constraint like, oh, x has to be larger than, or the vector x has to have a maximal L2 norm of 5 or anything. So it's just unconstrained optimization, and you can see it's foolproof. Fminunc, you supply g, you supply 0, which is the starting value, and you write the output into x and fval. Why? Remember, you don't only want to find x star, you will also want to know what is f of x star, f of x star at x star. And you can see Fminunc, if we start at 0, the result is 1.4883. Again, you can see, remember, the basic setting is 4 digits, so you will probably see more digits later on if you were to include the precision and the number of decimal points here. Fval is -18757, and this is the global minimum. Now, if we start somewhere else, if we start at 5, Fminunc, which is not a simple optimization tool, this is usually, as with all MATLAB functions, this is a set of optimization strategies and tools, and it will look at the function and decide on which algorithm to use, what we usually refer to as a tuned optimizer. And you can see Fminunc, using this different starting value, suddenly goes into x equal to 3.6437, and f at x star is -0.69, which is the local optimum, the local minimum. Bottom line, you have 2 starting values, you have a tuned, very sophisticated optimizer, and you will see that suddenly MATLAB is not able to distinguish between those 2 optima. It will depend on the starting value, even with these very sophisticated optimization tools. Now you can also have a function with several global optima. And even with local and global optima, the optimizer cannot distinguish between them. But with global optima, if you have more than one, it's quite clear that the computer cannot distinguish between the 2, because mathematically they are equivalent. They have the same, they share the same properties. So we have f defined again as polyval, and then it's a different polynomial, same thing here, and you can see we have 2 global minima at 1 and at 3. And again, depending on the starting value, you will find 1 or 3. With this function, it's quite simple. Again, what can you do if you want to make sure that this is a global minima? And if you have found all the global minimas, there is this one strategy that you can change. Or do you have an idea how you can look for different optima?
Was it the case that we look for one minimum and then just divide fx? Yeah,
it goes like this. A little bit different. Now, assume we have a polynomial. Very simple case of a polynomial. And you know, for example, this is a polynomial, and it has a global minimum at 1. Okay. How would you do it? Let me just think. So that means you can, yeah. Now I have to think about this a little bit more in detail. My first idea was to subtract f of x star at the minimum, or add it to the function. Then the new function has a root at this point, and then you can simply divide it by x minus the root, and what remains is a function that has one root less. Right now I'm not so sure whether this works. I have to think about this a little bit more. But with roots it works. If you want to find all the roots, you can simply take the roots, divide it by x minus 1 root, and then the function, the rest, will have one root less, and you can continue to find all the roots iteratively. But with minima, I have to think about this. I think there's something you can do about this. Now, this is not relevant for us here, but I wanted to tell you at least that we are just talking about finite dimensional problems and finite dimensional optimization. There are also in mathematics and optimization, there are problems which are infinite dimensional. What does it mean? It means that you have a solution of a vector, and you don't know how many variables are in this vector. The variable vector is infinitely dimensional, so you have x1, x2, x3, x4, and so on up until infinity. I haven't thought of any problem in economics or finance that actually generates an infinite dimensional optimization problem, but these are known in engineering, and I would assume in physics, and in these cases you need different optimization tools. But these things do exist. So you have an infinite number of decision variables. We don't need this here, but I wanted to make you aware of this. If you have constraints, you will no longer have an unconstrained optimization problem, but you will have a constrained optimization problem. And in this case, everything changes. Why? Remember what you've learned at school. You have a function that looks like this, and you were asked to find the local optima of this function. What did you do? You knew that in this very special case, the potential optima are those points at which the first derivative becomes 0. And then you have to check the second derivative of the function to make sure that this and this, these are local optima, and the third one isn't. But what happens if you have constraints on x? What happens? For example, if we assume x to be larger than, say, 1, and smaller than 1.3, and this here is the solution space. What does it mean? The information that the first derivative is 0 is of no use, no longer of any use. And it might just be that the local or global optimum is in a set of numbers at which the function's derivative is 0, but it might also be that the solution is on the edge of the solution space. And this is what happens almost all the times. If you have constrained optimization, you can no longer work with the derivatives. And this is also why it's left out. It's high school, probably. At least without, if you don't have a linear function. But in all other cases, with nonlinear functions, the regular optimization strategy to use derivatives is no longer of any use. What you can do is you can try to start at some point, and what you do is you use derivatives to go into the direction of steepest descent. This is the general idea I've told you about. If you have a plane like this, if you have a room, and you want to find the lowest point in the ceiling, you would take a ball and you would drop it, and it would go into the direction of the steepest descent. Simple result in physics. And then it would not matter how far the ball would go. It would either slow down in the minimum, or it would reach the edge. And if you know if the ball reaches the edge, which would happen at this point here, you start somewhere, you let the ball drop, and if it doesn't slow down, it simply goes down to the edge. You know that the global minimum, or local minimum at least, has to be on the edge of the solution space. So you need different algorithms, different strategies, and in MATLAB, usually you have Fminunc, Fmin function minimization constraint. This is a different function. And as a standard rule, all the constraints are interpreted in the form of less than or equal than. So you will have I just switch that. You have to minimize f, and x has to be smaller or equal than function g of x. This is how we do it. Or actually, what we do is we write it this even more simple. In some cases, optimization becomes quite simple. That is the case in convex or at least concave optimization. If the target function is convex and the permitted solution set is convex too, we call it a convex problem. And if f is convex, but the solution set is concave, it's called a concave function. What does it mean, a concave problem? In a convex problem, a local optimum is always a global optimum. So there are some cases, and actually these are theoretical and coming from microeconomics and also from portfolio optimization. In some cases you can show that, I know one example in portfolio optimization, it's quite simple. If in portfolio optimization you try to minimize the expected shortfall of a portfolio with a given return, with a given minimum return, you can easily show that the objective function is convex. And if that's the case, you know that if the function f and the solution set is convex, you know that any optimum you find, any local optimum, is also the global one. And then you can stop. You don't have to prove that the local optimum you found is a global one. You know that the first one you encounter is a global optimum. And this is quite convenient, especially in microeconomics and, as I said, in portfolio management. And in a concave problem, the global optimum lies on the edge of the solution set. So you also know. So what can you do? Optimization without constraints is actually quite easy. You can take the result from high school, you've known from the one-dimensional space, and it immediately translates into the n-dimensional real space. That is, if the target function f is convex and differentiable on the n-dimensional real space, f will have a global minimum in the vector f x star if and only if, that's the German genau dann wenn. So this equivalent, if we have the gradient, nabla, of f at x star is equal to 0. Actually, this has to be a capital 0, the 0 vector. What does it mean? The gradient is what? It's the vector of all partial derivatives. One has to be careful. In calculus, in n-dimensional real calculus, there's a difference between the derivative and the gradient. In many cases they coincide, they're the same, but in some cases the vector of partial derivatives is not equal to the derivative. But here we take the partial derivatives, the gradient has to be 0, so that means all the partial derivatives has to be 0. first partial derivative with respect to x1, with respect to x2, and so on. So what do? We actually take the same result from the one-dimensional case. Derivative has to be equal, and it simply means that in the n-dimensional case, all the n first partial derivatives have to be equal to 0. Again, the tricky part is here. You will remember this from high school. The problem is, in the n-dimensional case, f has to be convex for this to work. So the requirement is that f is a convex function. Otherwise, this will not work. So this is the first problem we have in n-dimensional case. Now, we distinguish between different types of optimization problems. First of all, we can distinguish between linear and differentiate between linear and nonlinear optimization problems. Linear is quite simple. If the objective function and all the constraints are given as linear functions, more precisely as affine linear functions, then it's called a linear optimization problem, or simply a linear program, or linear program. So LP program, LP problem, this is a linear optimization problem in which all the functions, the constraints and the objective function, are affine linear. Why is it important to stress that it's affine linear? Well, you're probably all studying economics, right? You're not from the math department. Okay. But has any one of you taken the bachelor here at Leipzig? Okay. If you had, I'm sure that our colleagues from the math department would have tortured you with the linear algebra in such detail that you knew what a linear function actually is. We all know linear functions from high school. A linear function from high school is a line in the real space. Well, in mathematics, it's not. It's much more general. A linear space in German, or a vector space, same word in German, Vektorraum oder Linearraum. A vector space in mathematics is just a set of mathematical objects of any kind, and you can define two operations on this set. First of all, you can define a scalar product. You can take a real valued number, and if you would multiply it with a vector and take this function f of av, you can take out the real valued scalar and put it in front, and this is equal. This is the scalar product. And you have to define a vector sum. If f of v plus w equals f of v plus f of w, and this is an operation that works, then these two operations, scalar product and vector sum, defined on a set of mathematical objects, then this is called a vector space, a linear space. And the real plane, the two-dimensional real space, is just one example in which these linear functions can be defined. Some trivial other examples of a linear space, polynomials. Polynomials are a vector space. If you have two polynomials, you can add them, and you get another polynomial, and you can take a number, for example, 5. 5 times x squared is 5 times x squared. It's also a polynomial. So the two operations, vector sum and scalar product, do not leave this set of objects you define. But that also means, if you look at these two definitions, this means that this function, f of x equal to a plus b times x, with two numbers a and b, this is not strictly a linear function. This is a linear function that has been translated to some place else. Because from this definition, these two definitions, the scalar product and the linear addition, the linear sum, it follows that all vectors have to go through the origin. They have to go through 0. So this is why, mathematically, strictly speaking, such a function that we would recognize this is a line, this is a linear function. This has to be referred to as an affine linear function. It is linear, but only in the sense that it's a linear function that has been transformed a little bit and translated in the space. Now, if all these functions are affine linear functions, it's a linear program. Has any one of you ever seen the simplex algorithm work, or linear program? This is usually part of the math introduction for business students. Linear optimization, it's quite simple. Who has not seen this in the bachelor's degree? You have all seen this? Sure. Okay. I can show you the basic result in a plot. Now imagine you have a function that looks like this. This is your objective function. Oh no, let's start. Let us assume x1, x2. Okay. You have two decision variables. You have two resources, and you want to produce a good. Let's say you can use capital and labor, and you have restrictions on capital and labor. Then these restrictions will be linear. That means, for example, you have one restriction that you can only use as much capital. So you will, these are all inequalities. So you would include a line and you would mark the space that is allowed. In this case, this space is allowed. Okay. Then let's include another restriction. Let's say this one. Let's assume we have another restriction that looks like this. And in the end, let's also make this. And in the end, you realize that the set of possible solutions has a very particular shape. And it's quite simple to show that if you do this, what will result is what? In German, it's a convex polyeder. I would assume that in English it's the same word. It's a convex polyeder. It's not a rectangle, but it's a convex geometrical structure. And convex means that you... Is everyone clear on what convex in this sense means? If you take any 2 points and you were to connect these 2 points, all the points on this connection line are also part of the set. So this one here, this is a convex, but this one here is not convex, because if you take this point and this point, the connection line, the connecting line, would include some points that are not part of this shape. And in this case here, the resulting solution set is convex. And this makes optimization quite simple, together with the fact that it's linear. Because if you were to solve this optimization problem graphically, what would you do? You would take the objective function, you would plot it through the origin, and then you would simply pull it out as far as you can, and then you would realize that at some point it just touches one single point, and this would be the case, for example, here, and this is the optimum. And there are several other possibilities. First possibility is that, for example, you get an objective function that looks like this, in which case all the points on this part here are optimal. This is the case of infinite solutions. And it might also be that there is not a single solution. This is simply the case if, for example, here you have two restrictions that are mutually exclusive. If you have one restriction like this and the other one like this, then the solution set is empty. So there are only three possibilities. One solution, no solution, infinite solutions. And you can solve any linear program graphically by doing this. And the simplex algorithm is actually a very clever way of testing all the corners iteratively, of going from one corner of this convex shape to the next one, and trying out whether one of these points is optimal. And it's quite simple and it's quite famous, the simplex algorithm. Okay. However, of course, as soon as the constraints or the objective function are not linear, you have non-linear optimization and this algorithm will no longer work. So this is only possible if all the functions, objective and constraints, if they are affine linear. You can do continuous versus discrete optimization and stochastic versus deterministic optimization. Stochastic versus deterministic optimization is quite clear. If the functions you are optimizing are random variables, you will get a stochastic optimization problem. It gets tricky then. So usually we'll only deal with deterministic optimization. Continuous versus discrete. We've only dealt with real values, vectors so far. So x was an element of the n-dimensional real space. But as soon as we argue that x is part of the normal numbers, of integers, or of the set of do you say full numbers in English? I would assume. Yeah? Ganzen Zahlen in German. Or the positive integers. You have a discrete optimization problem. One would intuitively think that this is simpler, because you have fewer numbers to look at. Quite simple. The set of real, I mean, it's a philosophical question, which set of numbers is larger. Obviously, the set of real numbers is larger than the set of integers. But both go to infinity, so again, this is a philosophical question. But it is obvious that the set of discrete numbers, of integers, is smaller. Then one might think that optimization is simpler. Actually, it is not. Discrete optimization is usually impossible to solve. Why? One of the famous examples for a discrete optimization problem is the Knapsack or rucksack problem one has. What is the problem? You have a volume in your backpack and you have certain objects with a certain utility. Could also have a certain profit attached to it. For example, I need this for my lecture, so the utility is quite high. I don't necessarily need this, utility is quite low. The problem now is I have to pack my bag. And if I include this, the bag is almost full, and I can only include a couple of pens. I cannot include the features, and I cannot include the computer at the same time. So I have to make a decision, and I cannot simply cut the tablet in half and include half a tablet in my bag. This makes it quite difficult to solve. And it is quite simple, it's quite simple to show that most discrete optimization problems cannot be solved in finite time. It's sometimes referred to as NP hard. NP difficult. If you ever have the pleasure of hearing a lecture on optimization and on complexity, there are huge research fields in mathematics and computer science that are related and that are working on this sort of thing. Because it means basically that if you were to solve one of these problems that are NP difficult, that are so extremely hard to solve, you would have found a solution to all difficult problems or problems that are that difficult. That means the usual setting is that you will not be able to find a solution to a discrete optimization problem. You can only find a good solution in finite time. But at some point you need to stop, and you need to be satisfied with the best solution you have found so far. And the examples for these discrete optimization problems, they're actually quite realistic, and they are taken from real life. The first one is the backpack problem, the rucksack problem. Knappensackproblem in German. The second one is the traveling salesman problem, TSP. A traveling salesman, it's also the same. A traveling salesman has, say, 5 cities he has to go to. There are distances he has to travel, and he needs to minimize the travel time or minimize the travel distance. He has to cover all 5 cities. The question now is which route to take. And this is the traveling salesman problem. It's also difficult to solve. Why? Because you cannot simply go halfway to the first city and then halfway to the second one. If you decide to go from Leipzig to Dresden, you have to travel the full distance. And then afterwards you have to face the distance from Dresden to, say, Berlin. This is the traveling salesman problem. And there are a number of other problems that are discrete in nature. This is, by the way, the foundation of operations research. Back in World War II, the Allied forces were concerned with strategies and optimization tools to optimize the routes for their ship convoys from the US to Europe, to UK, and to Russia. And they needed to optimize the travel routes and destroyer supply and destroyer support. They had only a limited number of destroyers, and they needed to distribute the destroyers to the different convoys, so to minimize the risk of losing ships to submarines and to maximize the deliveries to the UK and to the other allies. And this is how operations research came into existence, because people in the military started to look at algorithms with which they can solve these sort of problems. And nowadays, this has become management science or operations research, discrete optimization problems. Okay. Now, you now know that you have convex optimization, you have linear, non-linear optimization. Usually we'll deal with continuous deterministic optimization. When it comes to portfolio optimization, again, this is of course an unrealistic assumption, because in portfolio optimization, one would think that we need to buy whole numbers of stocks. We cannot buy 1.5 stocks. We need to buy 1 or 2, but usually you exclude this. You just assume that you're dealing in such large numbers. You're not buying 1 or 2, but you're buying 1,500 compared to 2,250 stocks. Then it doesn't matter. You simply round the numbers that result. Okay. And again, one has to keep in mind that at some points we'll have to deal with heuristics when it comes to discrete optimization. Okay. Now let's look a little bit at unconstrained optimization. Now, we cannot assume that we can find a global optimum. We have to assume that a local optimum is the best thing we can find, and most approaches are iterative in nature. And what does it mean? We have a sequence x, k, of approximations which are supposed to converge against the solution we're looking for, x star. So we have the first solution, the second one, the third one, and at some point we stop and we have a sequence, and the sequence should converge to x star. By the way, sequence in German is Folge. Okay. Now, we only consider minimization problems, because we know that maximization problems are equivalent to this. In order for the sequence to run in the correct direction of a local optimum, we assume that we should find a descent direction, xk, and a vector sk, so that the following holds. The function at xk plus alpha times s is smaller than f at xk, which means we have a solution xk. We want to improve on this solution. And how do we improve on this? We take a step length s and we go into the direction of xk with a step s, and maybe we take a full step, maybe we only take half a step or 1.5 step. And then for this new vector, we can see that f is smaller than f at the previous solution. Then, of course, xk plus alpha times sk is xk plus 1. This is the next solution, xk plus 1. And if this one on the right, this expression on the left-hand side, is smaller or equal than, we would say this is enough. We are not improving on our previous solution, we have to stop. And this basically is the idea that we are starting at some vector x, k, and we need to find a direction into which we want to go. We need to know how far we should go into this direction, and this should give you the next solution, xk plus 1. Again, this is very simple. This is a very simple idea, but later on we'll see how we can actually find these solutions. So if we write this function f at alpha equal to f at x plus alpha times s, a descent direction is characterized by what? We take the derivative of h with respect to alpha at alpha, then this is equal to the gradient of f transposed times the vector s, and this has to be smaller than 0. Then this means that this is a proper descent direction. Now, if necessary, it might be helpful to normalize this descent vector to length s. Then the optimization algorithm is simply given by, we have to find a descent direction. Remember this example of finding the lowest point in the ceiling. Simply take a ball, drop it to the ground, and it will fall into the direction of steepest descent. Now, later on, we will use as the descent function the derivative and the direction of steepest descent. But we could also take a different route. No? So we find a proper, actually decent is the wrong translation. I have to say a proper or a sensible direction, S. We have to find an increment alpha, update the solution xk plus 1 equal to xk plus alpha k times sk, and then abort as soon as we see the sequence to converge, as soon as the sequence converges. Okay. Now, as you can see, this is as far as I've gotten with the translation, and I will tell you a little bit about the next couple of slides, because those don't need to be translated. The question now is, how can you evaluate the efficacy and the suitability of these optimization algorithms? In many cases, you cannot. In many cases, especially when optimization gets difficult, long linear functions, especially discrete optimization problems, there is no way you can analytically show that an optimization tool, an optimization algorithm is working. You can only show that in this scenario with a convex function or with linear optimization, this algorithm works well. But in the general case, in n dimensions, you will have no tool and no result that tells you, yes, analytically, this algorithm always gives you a local optimum. But what you can do is, you can use test functions. And I want to show you these because before studying mathematics, I wasn't aware of this. All these functions are sometimes quite pathological in nature. That means you will almost never encounter them in real applications, but they are defined and they are engineered to be extremely difficult. This is why they're called test functions. And you can use these test functions as a worst case scenario, and you can use your algorithms on these test functions. And if your algorithms work well with these test functions, you know that they will work properly on any other given function. And don't let these functions fool you, and don't let the simple definitions of these functions fool you. You will see that these functions are quite simple when it comes to their definition, but the plots are quite colorful. The first one is the Ecklie function. It is defined in n dimensions by minus 20 times exponential function of minus 0.2 and then square root of 1/2 sum of xi squared minus exponential function 1/n sum and so on. Very simple. And if this function were given in one dimension, I would assume that you would at least try to solve this on a sheet of paper. You would try to solve for the first derivative, set it to equal, and I don't know, but it might work. The global minimum is at x equal to the 0 vector, and it has multiple local minima. Bird function. Sinus and so on defined in 2 dimensions here, 2 global minima at approximately with a function value of fx star equal to approximately minus 106.76 and so on. The Booth function, this one is actually pretty simple. Look at this. x1 plus 2x2 minus 7 squared plus 2x1 plus x2 minus 5 squared. One would think that this function doesn't deserve its own name. It actually does. It has a global minimum at 1, 3 and multiple local minima. Schwefel function. This one is, one can see that the square root of the absolute value of xi makes this one tricky, and it does. And it has a global minimum at xi equal to 420.96 and so on, transposed. And the function value is minus n times, so the dimension n times 480 and so on. Again, numerous local minima. This is the Ecklie function. I would suggest and I would encourage you to program these in MATLAB, because in MATLAB you can use the cursor and shift it around a little bit, and then you can see what horrible function these are. So this one, again, remember the Ecklie function. It has numerous local minima. Now, we can clearly see the global minimum, but all the optimization algorithms will have a hard time finding this one. And it's only by luck that you will find the global optimum, and in this spot you cannot see the local minimum. This one looks pretty smooth, it's not. Next one. Now, with this one, everyone can see that this is a very tricky function to optimize, to minimize. This is the bird function. Next one. This is, I've shown you 2 pictures, 2 plots from the side, and this is the Booth function. This is this one. Again, numerous local minima. Yeah? It looks pretty simple. It's a disaster for any optimization algorithm. And this is my favorite, the Schwefel function. This is just a mountainous region with a huge number of local and global, actually one global, but local minima and maxima. And now imagine an algorithm that works like the magical hand with a ball, letting the ball drop somewhere. You would immediately see that any strategy that tries to find a minimum by going into the direction of steepest descent will ultimately fall into one of the local minima. And again, the optimization tools you have, for most of them, you can only show for some special scenarios, in special cases, that they can find the global optimum and that they converge. And in many cases, you have no analytical result. You can only use test functions. You can run those algorithms on test functions. And if they do better than other algorithms, you know, okay, in practice, these will perform also. Actually, these test functions are not exclusively used for optimization. They are used in different settings in numerical analysis as well. Because as you can see, these are quite simple when it comes to their definition. Yeah, they take just one line, but it's a totally different story when it comes to optimization. Okay. Yeah. Because the slides are not yet translated, I will simply tell you a little bit about what we are doing next. We will next talk about gradient-based methods and the Newton method. And here you can see this one is the method of steepest descent. You take the gradient, again, you rely now on partial derivatives, and as the direction of descent, you take the direction of steepest descent. This will be the gradient-based method of steepest descent, and then you will get an optimization that looks like this. And this is actually, if you remember it, this is the Newton method in one dimension. Yeah? Fx is x minus, or x2 is x1 minus f at x divided by the derivative of x. Yeah? This is just the generalization to n dimensions. And later on, we will also see the Newton method is more elaborate in n dimensions. Here, this is the Newton method. It is a generalization, an extension of the method of steepest descent. And the extension is that you not only use the first derivatives, but you also use the Hess matrix, the matrix that includes the second derivative, second partial derivatives. So you have xk plus 1 equals xk minus alpha, and not just the gradient, but also the Hess matrix. And then you have an additional method at hand to optimize. And then later on, we'll talk about derivative-free methods. Those methods that are derivative-free, that do not use derivatives, are heuristic in nature. And what they do is simply try out solutions. And the simplest solution one can think of, and the simplest algorithm is, for example, let us assume I want to minimize the age of the students. What I can do is, what is the minimal age of all of them? I ask 2 persons, or let's say 3 persons, and let's say 20, 21, 23. I know 20 is the best solution, 21, 23, quite optimistic, I know. So 20 is the best solution yet. 23 or 22 is the worst solution. Then I will throw you out and I will ask someone else. Now you will tell me 24. No improvement, I will ask the next one. 19. So I have 20, 21, 19. You are now the best solution. 20, 21, now you are the worst solution. I will throw you out, ask someone else, try out a new solution. And this is in fact the derivative-free method, and the algorithm I will show you here. It's more sophisticated, it's tuned, but basically it's the heuristic idea of using a set of solutions, trying out the solutions, throwing out bad solutions, and trying out new solutions and improving on this vector of solutions. And then you simply calculate and calculate and calculate, and at some point you realize, okay, I can no longer improve on my best solution. And you can see on the slides, if you take the German set, This is the Nelder-Mead algorithm, Nelder-Mead, and you can see how this works. Use n+1 solutions, use another one, improve on this, mirror it, then again use a best solution, extend it, and all the steps in this algorithm are just very sophisticated ways of coming up with new potential better solutions. But the basic idea is still the same. Use n solutions, try out new ones, kick out worse ones, and then at some point stop. This is Nelder-Mead, and this is an algorithm that is very useful when you don't want to use derivatives. If you don't want derivatives for any kind of reason, if, for example, you know the function is not differentiable, and Nelder-Mead is, of course, also quite useful with discrete optimization. Yeah? And this is one possibility. And I will leave you with the last idea. Remember this idea here with the backpack. You remember that this is a discrete optimization problem. Now assume that I only have two objects. Now, in the worst case, I can always try what is called complete enumeration, full enumeration. That simply is the idea that if, for example, I have two objects and I can only use one, or I can only use one at the same time, I can simply do this, put the first object in the back, have a utility of 5. I take the second one, I have a utility of 10. Okay, the second solution is the best. The problem is, and this is why discrete optimization is so hard, you might know that with increases in the number of possibilities, this is a combinatorial problem, and the number of potential solutions is, it depends on the problem, is n factorial. So I can try out two things. Now, 2 factorial is 2 times 1, so I have 2 solutions. If I have 3 possibilities, I have 3 factorials, so I have 6 possibilities. If I have 10, I have 10 factorial, factor 10, factor 10, and then it no longer works. Yeah? I would have to try out so many possibilities that even computer cannot do it. But full enumeration is, of course, one possibility, and Nelder-Mead does nothing else, in fact. It tries out solutions, but instead of looking at all solutions, it just tries to look at a very good subset of all solutions, and it tries to look at a subset of solutions that is improved upon in each step of the algorithm. And it is not derivative based. It's not based on derivatives, and this is why this is a very good algorithm when it comes to discrete optimization. And at the end, you can see all this in MATLAB, and you can see how many functions in MATLAB fail, even in simple examples. And this simply illustrates the need to know about the shortcomings of these derivatives, because MATLAB at some point will tell you the derivatives cannot be calculated, or the derivatives are wrong, they are not accurate. Then you have to switch to another algorithm. Hopefully MATLAB will do it for you, but if not, you have to switch the function, or you program it yourself. But usually it should be in MATLAB. Okay. Do you have any questions? So I know what I will be doing this night. I will translate the slides for them to be ready tomorrow in the morning. But if you have no further questions, thank you for your attention, and see you tomorrow.